of this whole unit, conservation of energy, is the big concept you need to understand in order to be successful on the AP exam and just to know physics. Yeah. So if we look at work kinetic energy theorem, which we learned about before, that said work done by the net force is equal to change in kinetic energy. Well, we can take this work done by the net force and we can split that up into work done by non-conservative forces and work done by conservative forces. Right? And then moving the work done by conservative forces to the right side, I had to think that was right or left for a moment, gets us this. Right? And what is minus work done by conservative force? That's potential energy. So we can say that work done by non-conservative forces is equal to change in potential energy plus change in kinetic energy. This is kind of our big equation that we'll use for the rest of the unit. And the most important thing for you to know going into the AP exam. A bit of terminology. I mentioned this earlier in the unit, but just to remind you, kinetic plus potential added together is called, does anybody remember? Yes, is called mechanical energy. So, what this means is that any work done by non-conservative forces will change the mechanical energy of the system. Work done by conservative forces does not change the mechanical energy. Work done by conservative forces will cause energy to shift between kinetic and potential. Okay, does that make sense? So work done by non-conservative forces changes the mechanical energy of the system. Work done by conservative forces does not change the total mechanical energy, but it does cause energy to shift between potential and kinetic. Right. So again, for mechanical energy to remain constant, what needs to be true? What is mechanical energy? The sum of those two. So what needs to be true for the sum of those two to remain constant? Look at this equation. What needs to be true for the sum of these two to remain constant? Not change. Which means what about this? Yeah. So the total work done by non-conservative forces must be equal to 0 in order for mechanical energy to remain constant. The right side of this equation is just a change in mechanical energy. So if the right side, if our change in mechanical energy, if our mechanical energy is going to be constant, change in mechanical energy has to be 0, which means that the left side must be equal to 0 as well. So for today, we'll be dealing with situations where that is true, where non-conservative forces are doing 0 work. In general, you'll need to think, like today you might get into a pattern of just blindly saying, oh, energy is conserved, energy is conserved, energy is conserved. But remember that you need to, this condition needs to be met before you can apply energy conservation. If there is non-zero work being done by non-conservative forces, then you have to incorporate the work done by those forces into your calculations. Okay? Okay. So, if the work done by non-conservative forces totals up to 0, then we can say 0 equals delta K plus delta U, which means that the change in kinetic and the change in potential are equal and opposite. So meaning any increase in kinetic energy causes an equal decrease in potential energy and vice versa. There's an equivalent way of writing this that is sometimes useful. Generally, I think about it in terms of the other way of writing this. Anytime we have a delta something, how can we rewrite that? Right, final minus initial. And then if we move things to other sides, we can say the left side can become U naught plus K naught, and the right side can become U final plus K final. So this is an equivalent, these two are equivalent representations of the same idea of energy conservation. You can say initial energy equals final energy, or you can say change in kinetic equals change in potential negative. Depending on the problem, one or the other might be easier to think about, maybe just depending on you and how you think. Yeah. I will more often default to using this version, but that's just, it's a personal preference. Right. So yeah, another way of writing that, the book uses the symbol EMAC. So EMAC initial equals EMAC final if the total work done by non-conservative forces is 0. Okay. That condition will be especially important to remember as we move along and get to the AP exam, because there are a lot of different principles that we're going to have that we could apply to a given problem, and you need to know these conditions for when you can apply what stuff. Okay. So that's it for concept. The rest of what we have is just examples of this to work through, see how it plays out in different scenarios. So 22, ball is thrown from a height 3.5 meters off the ground. Speed when it hits the ground is 10.1 meters per second. What was its initial speed? Okay, well, we can use either version. Let's just use this one just because. So, minus change in kinetic energy. And what is change in kinetic energy? Change in kinetic energy? It's 1/2 mv final squared minus v naught squared. Is equal to change in potential energy, which is mg delta y. There's no spring involved in this problem, so we only have gravitational potential energy to be concerned about. What do you notice? Yeah, bless you. It's just like this equation's on a diet. Mass goes bye-bye. And then we can plug in and solve. So we got minus 1/2. V final is 10.1. V initial is what we're trying to find. Equals G is 9.8. What's delta y? Right? Spinning downward. So our displacement is negative 3.5. Yeah, and then we can solve. Actually, before we do that, does this look familiar? Yeah, look, that's the time-independent equation. Whoa. What? That's the time-independent equation, which is interesting. Mass cancels out. And an interesting point of note, using energy conservation, when we did kinematics, we used components and calculated like the magnitude and direction of the final velocity. Well, it turns out the magnitude of a final velocity does not depend at all on what direction the initial velocity was, because the energy is a scalar. So if it's going at some speed at an angle upward, that's the same as if it's going at the same speed at the angle downward in terms of kinetic energy. So the speed as it hits the ground does not change based on what angle you're throwing something at. It will change the direction of the final velocity, but not the magnitude. And then we can calculate away. And get 5.8. 5.78 meters per second. All right. In the interest of time, because I'm going to be gone next class, and you guys are going to do a lab, so I want to have time to explain the lab to you. So in the interest of time, I'm going to do all your calculating for you today. Yay! All right. Block slides from S down a frictionless inclined plane, angled at 24 degrees above the horizontal. What is its speed when it has traveled 22 meters? Well, frictionless. So what forces are acting on this block? Gravity and normal. Uh-oh. Is normal conservative? No. Is that a problem?
No.
Can we decide?
No.
What direction is the block moving?
Down.
Not down. Down the plane. What direction is normal force? No. Perpendicular to the plane, which means it's perpendicular to the displacement, which means it does zero work. So even though there is a conservative force acting, we can still apply conservation of mechanical energy. So you can say minus delta K equals delta U. And we can just plug in for that. And look, how about that? Chunk, chunk. Fun fact, as long as there are no non-conservative forces acting, all that matters is the change in height. It doesn't matter if it's flying through the air at different angles. It doesn't matter if it's sliding down a ramp. It doesn't matter if it goes around a loop on a roller coaster. Like, if the energy is conserved, all that matters is the change in height. It doesn't matter how you get there. Gravity is conservative. Yeah. So I'm saying there are only conservative forces doing work. The work done by non-conservative forces is zero, so we can apply energy conservation. So, from rest, what does that mean? You know, zero. Final is what we're trying to find. G is 9.8. What's delta Y? Almost. What direction is the block moving? Down. The delta Y is down. The Y component of the displacement is downward. So negative. And then that's good because our negatives cancel out. We don't have something squared equals a negative. And I will quickly calculator for you. We get 13.24 meters per second.